Hello student, we are seeing the physics lecture, myself Rajesh Lagat. We have to see here the physics first chapter, rotational dynamics. This is the video number 8 and we have to see here the next topic, very IMP topic, the expression for torque in terms of moment of inertia. On that session, you have to ask the question in your board theory exam. Derive the relation between torque and moment of inertia and angular acceleration. This relation is nothing but the tau is equal to I alpha, where tau is the torque, I is the moment of inertia and alpha is the angular acceleration. In this way, you have to ask this question or also derive the expression for torque in terms of moment of inertia. For that purpose, we have to see here again the rigid body. If you have to apply the torque to that rigid body, then this rigid body which can be rotate about its axis with the constant angular acceleration alpha. If you have to apply the torque on that rigid body, then this rigid body can be rotated with the constant angular acceleration alpha. Suppose that this rigid body which is the consist of the n number of the masses m1, m2, m3 dot dot mn and situated at a distances r1, r2, r3 dot dot rn from the axis of rotation, which is also as shown in figure. All these axes which are passing through the point O, you have also seen in this diagram, all these axes which are passing through the point O and which are perpendicular to the plane of this figure. We have to see in also in the expression for the kinetic energy of rotating body. We also see this same diagram, but in this diagram we have to say here, if the torque is applied to that rigid body, then and then this body can be rotated, but what? With the constant angular acceleration alpha. In kinetic energy, we have to see that the body rotates with the constant angular velocity omega, but in this, by applying the torque, that rigid body which can be rotated with the constant angular acceleration alpha, you have to remember this. Then this body is consist of, we have to say here, the n particles of masses m1, m2, m3 dot dot mn situated at a distances r1, r2, r3 dot 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 rn from the axis of rotation. Okay. Then we have to turn for this mathematical expression, we can take the one condition here. As the body rotates with the constant angular acceleration alpha, then its linear acceleration for the first particle which is given by. In kinetic energy, we have to say same sentence, but change is what? As the body rotates in kinetic energy, rotating kinetic energy, as the body rotates with the constant angular velocity omega, then we have to take here the linear velocity at the time. In this expression of the torque, we can say as the body rotates with the constant angular acceleration alpha, then we have to take the linear acceleration for the first particle is given by. As the body rotates with the constant angular acceleration alpha, then its linear acceleration for the first particle is given by, and that is nothing but this relation. We know that A1 is equal to R1 alpha. You can also write this A2 is equal to R2 alpha. Alpha is a constant, therefore we can write simply alpha, not 1, 2, 3 or dot dot. But according to the Newton's second law of motion, we know that Newton's second law of motion, F is equal to ma. According to this, we can say here the F1 is equal to m1 a1. For the first particle, mass is m1 and linear acceleration is a1. Therefore, we can write here according to the Newton's second law of motion, force for the first particle of mass m1 and linear acceleration a1, which is given by F1 is equal to m1 a1, which is also as shown in figure. This is the this m1, then the force we can write here m1 a1 is also as shown in figure. We have to also substituting this value instead of this a1 is nothing but what? R1 alpha. Then substituting a1 is equal to R1 alpha in this equation, we can write F1 is equal to m1, and instead of a1 we can write what? R1 alpha. Therefore, F1 is equal to m1 R1 alpha. Similarly, you can say also for F2 second particles, the force acting on that rigid body, which is given by F2 is equal to m2 R2 alpha. Understand this? According to the Newton's second law, F is equal to ma. Therefore, F1 is equal to, for the first particle, F1 is equal to m1 a1. Substituting the value of a1 R1 alpha, we get F1 is equal to m1 R1 alpha. Also, F2 is equal to m2 R2 alpha. Then we have to say here, torque is act on that rotating body. Therefore, the torque about this axis of rotation, which is given by the definition. We can see this definition in 11th standard. Torque is nothing but what? Torque is the product of force and the moment arm. That moment arm is nothing but what? This is the perpendicular distance, which can be as shown in figure. Torque is nothing but it is the product of force and the moment arm. We know that force F1, F2, F3 dot dot, and moment arm, this is nothing but the perpendicular distance R1, R2, R3 dot dot Rn. Therefore, in symbol with terms we can write here τ1 is equal to F1 into R1. We can write here τ1 is equal to F1 into R1. This is for the first particle. Torque can be given by, according to the definition, torque is nothing but it is the product of force and the moment arm. Therefore, τ1 is equal to F1 R1. Instead of F1, we can write this value m1 R1 alpha. Substituting this value instead of F1, we get τ1 is equal to m1 R1 alpha into again this R1. This is the moment arm or the perpendicular distance. We can underline this R1. Instead of this R1 into R1, we can write simply R1 square. Therefore, τ1 is equal to m1 R1 square alpha. Understand this? Please see again. Torque is nothing but the force into moment arm. τ1 is equal to F1 into R1. Instead of F1, we can substitute m1 R1 alpha. Therefore, τ1 is equal to m1 R1 alpha into R1. R1 into R1, R1 square. Therefore, τ1 is equal to m1 R1 square alpha. Similarly, we can find out this τ2 is nothing but m2 R2 square alpha. τ2 is equal to m2 R2 square alpha. Also dot dot τn is equal to mn Rn square alpha. τn is equal to mn Rn square alpha. From this relation, we can write the total torque act on that rigid body, which can be rotated about its axis, and this total torque which can be given by the τ is equal to τ1 plus τ2 plus dot 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 τn. And substituting all these values of the τ1, τ2, we can write τ is equal to m1 R1 square alpha. We can find out this τ1 is equal to m1 R1 square alpha, τ2 is equal to nothing but what? m2 R2 square alpha, dot 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 τn is nothing but what? mn Rn square alpha. Therefore, we can write here τ is equal to m1 R1 square alpha plus m2 R2 square alpha plus dot 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 mn Rn square alpha. And from this, alpha is the common, and we can write here τ is equal to, in bracket, m1 R1 square plus m2 R2 square plus dot 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 mn Rn square, and common term, this is nothing but the alpha. Then this bracket term shows, we have to see here, you are known that terms m1 R1 square plus m2 R2 square dot dot mn Rn square. This is nothing but the definition of moment of inertia, and we can write here τ is equal to summation I is equal to 1 to n mi Ri square and into alpha. This is the common factor. Therefore, this mi Ri square, again you see that this is the definition of mi. It is the sum of product of mass of each particle and the square of distance from the axis of rotation. This is nothing but the mi denoted by letter I. Therefore, we can write here τ is equal to I into alpha, and this is nothing but the expression for the torque in terms of moment of inertia, and also this is the relation between torque and the angular acceleration alpha. τ is equal to I alpha. This is the very important form in the rotational dynamics. On this formula we can solve the numericals and also in applicable form, so that you can just practice this expression. This is asked in your board paper. Derive the expression for the torque in terms of moment of inertia, or derive the relation between the torque and angular acceleration. If you understand, okay, thank you.